This is an introduction to the National Semiconductor LM3424 controller for LED drivers with thermal foldback. Welcome to the training module on the LM3424. This training module introduces in detail the LM3424 controller for LED drivers with thermal foldback. The LM3424 includes a thermal foldback for temperature management of the LEDs. The LM3424 LED driver has a wide range input voltage from 4.5 volts to 75 volts, which makes it ideal for use in many illumination applications and other LED applications. Adjustable high-side current sense voltage allows for the tight regulation of the LED current with the highest efficiency possible. Additional features of the LM3424 LED driver are high-side adjustable current sense, a 1 amp peak MOSFET gate driver, input under voltage and output over voltage protection, pulse width modulation and analog dimming, cycle-by-cycle current limit, programmable slope compensation, programmable synchronizable switching frequency, programmable thermal foldback, programmable soft start, precision voltage reference, lower power shutdown, and thermal shutdown protection. The LM3424 device can be used as a LED driver, which can be configured as a buck boost, and SEPIC topology. Also in the automotive field, this can be used for headlight and general illumination. The controller has a wide input voltage range, allowing for the regulation of a variety of LED loads. The high-side differential current sense with low adjustable threshold voltage provides an excellent method for regulating output current while maintaining high system efficiency. The output enable-disable function, coupled with an internal dimming drive circuit, provides high-speed pulse width modulated dimming through the use of an external MOSFET placed at the LED load. This page gives typical performance characteristics of the LM3424 device, where boost efficiency versus input voltage and buck boost efficiency versus input voltage is plotted. Current regulators can be designed to accomplish three basic functions: buck, boost, and buck boost. All three topologies in their most basic form contain a main switching MOSFET. Peak current mode control is used by the LM3424 to regulate the average LED current through an array of high brightness LEDs. This method of control uses a series resistor in the LED path to sense LED current. Thermal foldback combats the high temperatures that LEDs can reach as a result of environmental conditions. When LED temperatures rise above a safe threshold, the lifetime and efficiency of the LED decreases. With the LM3424, lighting designers can program temperature and slope breakpoints within which the LEDs operate safely. When an overtemperature condition occurs, the LM3424's thermal foldback circuitry reduces the regulated current through the LEDs. The reduced current dims the LED to a range programmed by the designer, and the LED remains within the range until it returns to a safe operating temperature. Analog dimming applications require a lower switching frequency to minimize the effect of the leading edge blanking circuit. As the LED current is reduced, the output voltage and the duty cycle decreases. Eventually, the minimum on time is reached. The lower the switching frequency, the wider the linear dimming range. The LEDs cannot dim completely because there is always some resistance causing signal current to flow. This method is also susceptible to noise coupling at the CSH pin, since the potentiometer increases the size of the signal current loop. The LM3424 achieves peak current mode control using a comparator that monitors the main MOSFET Q1 transistor current, comparing it with the COMP pin voltage as shown. There are two possible methods to sense the transistor current. The RDS on of the main power MOSFET can be used as the current sense resistance because the IS pin was designed to withstand the high voltages present on the drain when the MOSFET is in the off state. Alternatively, a sense resistor located in the source of the MOSFET may be used for current sensing. However, a low inductance ESL type is suggested. The cycle-by-cycle current limit, ILIM, can be calculated using either method as the limiting resistance RLIM. The LM3424 control loop is modeled like any current mode controller. Using a first-order approximation, the uncompensated loop can be modeled as a single pole created by the output capacitor, and in the boost and buck boost topologies, a right half plane zero created by the inductor, where both have a dependence on the LED string dynamic resistance. Since ceramic capacitance is recommended for use with LED drivers due to long lifetimes and high ripple current ratings, the ESR of the output capacitor can also be neglected in the loop analysis. The LM3424 includes a high voltage, low dropout bias regulator. When power is applied, the regulator is enabled and sources current into an external capacitor, CVYP, connected to the VCC pin. The recommended bypass capacitance for the VCC regulator is 2.2 microfarads to 3.3 microfarads. The output of the VCC regulator is monitored by an internal UVLO circuit that protects the device from attempting to operate with insufficient supply voltage, and the supply is also internally current limited. The LM3424 can be configured to detect an output or input overvoltage condition via the OVP pin. The pin features a precision 1.24 volt threshold with 20 microamps typical of hysteresis. When the OVLO threshold is exceeded, the gate pin is immediately pulled low, and a 20 microamp current source provides hysteresis to the lower threshold of the OVLO hysteretic band. The NDIM pin is a dual-function input that features an accurate 1.24 volt threshold with programmable hysteresis as shown. This pin functions as both the pulse width modulated dimming input for the LEDs and as a VN UVLO. When the pin voltage rises and exceeds the 1.24 volt threshold, 20 microamps typical of current is driven out of the NDIM pin into the resistor divider, providing programmable hysteresis. The active low NDIM pin can be driven with a pulse width modulated signal, which controls the main NFET, and the dimming FET, dim FET. The brightness of the LEDs can be varied by modulating the duty cycle of this signal. LED brightness is approximately proportional to the pulse width modulated signal duty cycle. This function can be ignored if pulse width modulated dimming is not required, by using NDIM solely as a VN UVLO input, as described in the Input Under Voltage Lockout section, or by tying it directly to VCC or VN. This page gives information about design considerations of the LM3424. The main components that should be addressed while designing are the inductor L1, the input capacitor CIN, the output capacitors CO, the recirculating diode, and the dimming MOSFET. This page gives schematics of a buck and boost regulator topology using the LM3424 device. In buck regulator, the Vin is greater than the Vout, and in a boost regulator, Vin is less than Vout. This evaluation board showcases the LM3424 NFET controller used with a boost current regulator. It is designed to drive 9 to 12 LEDs at a maximum average lead current of 1 amp from a DC input voltage of 10 to 26 volts. The evaluation board showcases many of the LM3424 features, including thermal foldback, analog dimming, external switching frequency synchronization, and high-frequency pulse-width modulated dimming, among others.